Thank you. Good morning. Honored to be here again at Hackaday. And today I'm going to tell you about receiving signals from deep space spacecraft. I do want to tell you that I am not the first by any means to do this. And there are great people in this community. It's small, but great people who are very willing to help out, and I'm going to name drop a lot because they do deserve the credit for doing that. And one of them, Ivan Cardona in Spain, mentioned that receiving signals directly from the spacecraft is one of the only ways in which amateurs can have a direct connection with the planetary exploration programs. Yeah, you can see a lot of the information on NASA's website, but I'll show you that there is interesting information that you can get yourselves straight from the spacecraft, and it's interesting to analyze. It's sometimes very useful citizen science. So this is my backyard. And yes, you can see it from the sidewalk. So among my neighbors, these are the two theories of what goes on in my basement. Although in reality, what happens in my basement is a lot more like this. It's really watching grass grow. And I think that this is a really good analogy, because what I'm looking for is for a very specific blade of grass to be growing there in the spectrogram. There is the signal that is being received from a spacecraft somewhere in a planetary probe. The real DSN, the Deep Space Network, is a network of stations that NASA has around the globe. They're separated at 120 degrees so that there's constant view of the deep space. And they operate 70-meter dish antennas. ESA, the European Space Agency, as well as other space agencies around the world, operate similar tracking stations for their spacecraft. So let's take a look at what is the essential problem of the technical problem that we're trying to solve, and what is at the core of this concept of receiving space probes. Let's take as an example Juno, which is a space probe that is orbiting Jupiter for already a couple of years now. And the spacecraft has a transmitter which transmits 28 watts nominally, and it feeds the 28 watts into a 2.5 meter dish. Signal travels an average of 715 million kilometers to Earth. So that's the big problem. The big problem is that 288 dB path loss. NASA has a 70-meter dish with 68 dBi gain. So they indeed receive that signal with around minus 131 dBm, and getting into cryo-cooled amplifiers and very, very nice signal processing. They're able to recover the signal. They transmit in the range of 50 to 60 kilowatts with that antenna commands back to the spacecraft. With my 3.5 meter dish, however, in theory, that would have a 47 dBi gain, so my received signal in theory would be 152 dBm minus, but my dish is nowhere near ideal. So I have a very, very small signal to be picking up, and hence what we typically try to receive in amateur DSN is that signal there. So let me compare that to what would be received from a different type of dish. AMSAT in Germany, AMSAT is the Amateur Satellite Society, has a 20-meter dish that they share with the Bochum Observatory. With that 20-meter dish, they receive a 30 dB signal above noise, for example, from this one spacecraft. Specifically, this one is Tianwen-1, the Chinese Martian spacecraft. It's one of the strongest signals out there. And they can see the sidebands. You can see the modulation sidebands there. With a small dish, with a 3.5 meter dish, this is what I can receive. So it's only the residual carrier that we can receive with the small dishes. And we can see the carrier, and what we see is the interesting Doppler there. We'll talk a little bit more about that. So it's important to remember that what we can receive with small dishes is the residual carrier. So we're doing more detection than receiving signals. And how do we actually know that what we see is a spacecraft? So couple ways. Here I have, again, Tianwen-1 on this side, and just for the demonstration, I turned on a GPS-locked oscillator transmitting very close by in my basement, so a very weak signal, very similar in amplitude to the signal that is being received from Tianwen-1. And you can see a couple of interesting things between the two signals. Local interference does not have Doppler. The Doppler changes with spacecraft that are moving away or coming towards us. In addition to that, if you ever watched the movie Contact, what they did there is, like, when they were looking at that alien signal, is move the dish a little bit away and the signal disappeared, move it back, and you should get the signal back. So the contact maneuver, signal goes away if you just move the dish to the side a little bit, comes back if you move it back to the in the direction of the space probe, but local interference remains constant. I was telling you that you usually receive only the residual carrier. That is not always the case. When the spacecraft are really near Earth, for example, just after launch, and I'm talking about just 2-3 days after launch is the window, or when spacecraft have, because of their path, some proximity with Earth, but they are already on their high gain antennas, you're able to pick up enough of the modulation sidebands that you are able to decode and demodulate and decode the signals. For example, signals there from Tianwen-1 received on its way to Mars. You can clearly see the modulation sidebands. This is a Stereo A spacecraft, which just this August came by very close to us. 8.3 million kilometers is very close when the high gain antenna is being used. And we could decode pictures from that. I'll show you some of those. So where does this activity happen? There are a couple of bands. There are a couple of bands also in the KKA region, but most of the real activity that amateurs can look at happens in the X band and in the S band. So we're going to concentrate on S band and X band. We're trying to pick up the signal that is coming from the spacecraft to Earth. So that happens in S-band in 2.29 gigahertz, and the center of the band there for X-band is 8.45 gigahertz. I also put in this band here, the military X-band, which is used mostly for geostationary and geosynchronous military satellites, where they have their beacons, because these are really nice beacons to be able to tune the antenna system to. So this is where the activity happens. S-band is used mostly for nearer spacecraft, stuff that is in lunar orbit or parked at the Lagrangian points, while X-band is really where the DX, the long-range activity, happens. So very basic view of a station. You have some type of dish that is going to concentrate the signals onto a feed. When you're looking at S-band, most receivers and the higher end SDRs are able to tune into the S-band. So a down converter is not necessary. In the X-band, where the real activity happens, you definitely need a down converter that is placed very close to the feed, so that you're able to pick up those signals, and cable at the X-band attenuates terribly. So just little pieces of centimeters long of cable attenuates terribly. So you want to down convert that to something that you can send down the line into the house and be able to pick it up with a radio or with an SDR. The Doppler that I was showing you is in the audio range. So you don't want the radio wandering around in its frequency, so you have to lock the receiver and the down converter to some form of atomic clock. GPS disciplined oscillators are the easiest thing. And then you want to display the signal on some form of spectrogram to actually see the signal. The spacecraft are pretty far away, so you want to point the antenna directly at the spacecraft. To do that, you do need an automatic system with a rotator, and the information for where to point this, you can download it from the JPL. The JPL gives you the ephemeris data for pretty much every spacecraft. This is what it looks down there in the basement. So yeah, no spies or aliens, I promise, down there. The most visible piece of the system is, of course, the dish. And there are dishes that some of my colleagues use. For example, Scott Tilley has that little 70 centimeter MLD. He calls it the mighty little dish. Truly has done wonderful stuff with it on the software side. And you have different types of dishes. On the larger side for amateurs, 3 meters or 3.5 meters. Paul Marsh in England, I think that he is the granddaddy of picking up signals in from the DSN. Outstanding resource for anyone who wants to get into this. Then there are some amateurs who also have access to semi-professional dishes. For example, the AMSAT dishes. The AMSAT dish there in Bochum is a 20-meter dish. That's a pretty nice-sized dish. And also the 6.1 meter dishes of the Allen telescope array that belongs to SETI. Some amateurs have access to that. And then the big boys, as I was telling you, they use 70-meter dishes in the case of NASA and 35-meter dishes in the case of ESA. So you might want to remember from your classes back then that the bigger the dish, the higher the gain. But the way in which you actually get that gain is by narrowing the beam width. So a small dish, like a 0.6 meter dish, is going to have a half power beam width of around 3.57 degrees. So you want to be able to point towards the spacecraft, and you want to do better than half power, because half power is minus 3 dBs, and when you see those signals, that's small. But you're able to point it by hand. On the other hand, a 70-meter dish like NASA, they have to be moving those beasts with millidegree accuracy. So what is the best dish to choose for this? The best dish is the largest dish that you can point accurately. If you cannot point accurately. So how to point them? You do use rotators. For his mighty little dish, you can, Scott uses just a telescope mount, an ASL telescope mount. He in fact has a camera mounted next to it because he likes to track satellites and find zombie satellites. Really fascinating stuff that he has done on that. For my 3.5, for the 1.2 meter dish, I use just a Yaesu ASL rotator. Bang bang rotator, not super precise, but for 1.2 meter it's enough. For the 3.5 I use a speed rotator, but not with their stock pointer, with their stock controller. Interestingly, lately these rotators here, which are used for solar array tracking, have been coming out of China. They're pretty heavy duty, can move very large arrays for tracking the sun. So these have been starting to get common to move large dishes, relatively inexpensive and really, really heavy duty. Or you can have, like Scott also uses in his 2-meter dish, a heavy-duty ASL or pan-tilt camera mount, which now with the smaller cameras that outperform the huge cameras that were needed back then, those things are available in the surplus market quite a bit. So now we're moving the dish. How do you actually figure out where to point it? And that is requires heavy calculations and modeling, which fortunately JPL will do for you. You just tell the JPL Horizon system what spacecraft you want to track, and it will spit out a table for the day or whatever time span that you want, which contains right ascension and declination, which are ways of expressing coordinates in the sky. You can translate that through easy equations into azimuth and elevation for your location on Earth. It will tell you what is the distance from you to the spacecraft in astronomical units, and it will tell you what is the velocity. And the velocity is important because the velocity is going to tell you what is the Doppler that you're expecting from the spacecraft. So you can figure out from knowing the frequency of the spacecraft, where do you actually expect to receive it in your receiver. When I was originally doing this, I had to go through the calculations of the azimuth and elevation and then feed them into some program for the rotor control myself. But coincidentally, more or less at the same time, Buddha Y03DMU in Romania, he has this excellent program called Ph.D. rotator that knows how to control your different rotators, and he added this nifty utility in there where you give it the code of the spacecraft, so the ID number of the spacecraft, and it will go and fetch the data from JPL and control your dish to move the dish to the right position. Truly amazing stuff. In addition to that, if you know the frequency at which the spacecraft is transmitting and you know the LO of your down converter, then it will tell you at what frequency you should be expecting to receive that spacecraft. So really, really neat utility. How do you find out what are the frequencies? Well, everyone registers their frequencies from the ITU, the International Telecommunications Unit. But if you actually try to find the frequency from the ITU, not an easy thing to do. And there are nations like China that for some reason like to obscure where they're going to put it, although we amateurs can find out the frequency in just a couple of hours of observing. So I don't know why they do it, but the easier way, at least for NASA and ESA spacecraft, is to go to the Australian Telecommunications Authority, which actually gives the permission to the station in Nunorcia or the station in Canberra for the frequencies that they're going to use, and they give you the exact frequency at which the spacecraft is transmitting. You know the velocity of the spacecraft, you can calculate the Doppler, you know exactly where to find the spacecraft. And both NASA and ESA through the DSN Now and ES Track, they will tell you which spacecraft they are communicating with from which station right there. So you know that that spacecraft is actually active. In fact, sometimes you want to take a look at the wiggles, whether they're going up or coming down, because when they're coming down and they're using high rate telemetry, then that means that the modulation for that high rate telemetry is stealing from the main carrier, so your residual carrier is going to go down. So sometimes the best time to look for it is just before, just after they communicated with it, but they're still tracking it and locked to it. That's when you're going to have power in the residual carrier to be able to see the signal. Easiest stuff to pick up is S-band. First experiments that I did on it back in 2019, 2020 were with S-band, so built just a small helical antenna, helical feed. The transmission done by spacecraft is done in circular polarization. And in S-band, as I mentioned, you don't need a down converter if your radio is able to receive in that frequency. I do have a lot of junk around the house from cell phone towers, from ovens, etc. When you're trying to receive signals in the minus 130, minus 140 dB range, yes, all of those microwave ovens and cell phone towers are fully within spec, but they produce spurious stuff, which is very small, but very significant in the range that we're trying to pick up. So I did find a cavity filter on eBay. These seem to be used for filtering telemetry from aerospace type experiments. They're not expensive, and I've seen them quite a bit on eBay. So it cleans up the signal beautifully. LNA at the low nose amplifier up front at S-band is very easy. Just there are plenty of low noise amplifier offers from the Far East or from mini circuits, and just use something to follow it. And these are some of the results at S-band. So at S-band, as I was mentioning, you have a lot of lunar probes and spacecraft that are parked at the Lagrange points, observing space or observing Earth, observing the sun. And you have a couple of things here, like the Chinese relay satellite, the X-ray observatory. This is parked at Lagrange, and this is parked at Lagrange and the wind. And it's a very nice, easy start. All of these were done with the 1.2 meter dish, so a very easy way to get started into this and develop the technology. The real DX happens in X-band, and X-band is very neat because X-band is around 3 centimeters, so stuff that you can make out of just pipe, copper pipe bought in the store, works great. Jason Myers, KC2TDS, sitting here, built this feed horn. It was almost confiscated by TSA once when we took it down. I guess that you could use this as a blunt weapon, but visiting the Home Depot aisle where they keep the copper pipes, and the guy comes and asks you if you need some help, it's like maybe not. So it's very easy to build these stuff, very nice to build it, but it does take some accurate measurements. So again, Jason loves to play with his VNA and carefully cut a probe for this feed horn. And what you see in that feed is that there are these interesting blocks here, these copper blocks. Those squeeze the tube at some point. So the signals, as I was telling you, are polarized, circularly polarized. So you don't have to track. These spacecraft can be in any position relative to you. Circular polarization is going to be able to be picked up just by having the correct polarization on your antenna. And those blocks, what they do is they depolarize the circular polarization from the signal and turn it into linear polarization that you can now pick up with just a little probe. And the position of the probe is very important because that is going to define whether the signal is picked up in left-handed circular polarization or right-handed circular polarization. Most spacecraft transmit right-handed circular polarization. So it is reflected by the antenna, turns into left-handed circular polarization, and then you pick it up with your little probe. There are some exceptions. The Emirates Mars mission, as well as the Voyagers, they transmit in left-handed circular polarization. And this slide shows how important it is to choose the right polarization. The signal is small. You have around 3 dBs over noise floor here when it is being picked up in the right polarization. If you switch the polarization to the opposite polarization, you're going to lose the signal completely. So I have mounted on my dish a feed horn that has both left and right-handed circular polarization, low noise amplifiers very close by, and the down converter mounted right there. This is the homemade down converter. I can choose polarization based on which one of the two LNAs I'm picking out from. That is the feed horn. These are the LNAs, and go into two different down conversion paths. One is specifically for the DSN band, and the other one is for the MILSAT band. And I take the signal out in the 1450 megahertz, so that will easily go down a cable. If you don't want to build your own down converter, there is a down converter made by Kuhn in Germany. They make a wonderful low noise amplifier. And when I tried one of my colleagues' down converters, I didn't quite like it. It had a lot of birdies. The signal was noisier than with my own down converter. So I'm going to stick with my own down converter. How do you actually look at the performance of the antennas? We were just talking this morning, Vlad, about evaluating the performance of the antennas. And one of the best sources to be able to compare this antenna to that antenna, this antenna to my colleagues' antennas, is pointed at the sun, pointed at the moon. This is a really good way of looking at it. So if you point it at the cold sky is where you don't have really much stuff going on in our galaxy. So you're not pointing it at the center of the galaxy, which is this huge source of RF. But you're pointing it at cold sky. You get some baseline level, and then move the antenna and peak it at either the sun. So my antenna receives around 10 dB, the 3.5 meter dish, 10 dB of sun noise, and I get the moon at around 1 dB. So this is just because they're hot black bodies in the sky. And this is the first thing that tells you how well your antenna is doing. So the 3.5 meter dish, 10 dB, not a good signal. I would have expected a 10 dB sun noise more from like a 2.4 meter solid dish. So these dishes that are made for TV receive only in C band, they're pretty leaky at X band. But my dish performs superbly well for Earth, Moon, Earth, for moon bouncing. So it's a compromise. But this is a way of actually comparing signals. The other thing that I was telling you is like, why put the MILSAT band, the military satellite band on a dish, is because there you have an object in the sky, which is a far field point that stays in the right position the whole time, and you can easily move to it, and you can always compare day to day the beacon. So I have some favorites that I have very visible on my sky there in New Jersey, Canadian satellite, and one of the global SATCOM for the Air Force that provides signals that I can trust and I can use in order to tweak my antenna. So let's look a little bit at the signals that received with this originally. And these I received back in 2020. So you have signals coming from Bepi Colombo. So those are small numbers, these 137, 190 million. Those are relatively easy to pick up. That is the type of signal that you can see from those spacecraft. And you have some of the Martian satellites here. The Martian satellites are also interesting. They behave in a very interesting way as they are moving around the planet. By the way, you do not pick up the rovers. So once they land, the rovers transmit up to a relay network. And the relay network is what you can listen to. Currently there are 4 or 5 satellites. We invaded Mars in March, in July 2020. If you remember what we were doing in July 2020, we had a lot of time in our hands. So this was a really neat time to be tracking spacecraft. And here's what I was telling you that you can see, besides just that little carrier and detecting some faraway spacecraft, you actually can see things, right? You can see there the wiggles on that 2020 Perseverance spacecraft as it was launched. And what you see in the wiggles is that it's rotating. So there have been spacecraft where they have been rotating, and the spacecraft actually is out of control, that amateurs can pick up before the nations actually say, yep, we kind of lost that one. The Tianwen-1 is a very powerful transmitter, and this is China's mission to Mars. And Daniel Esteves, he loves to do decoding of these signals. And so he wrote a decoder in new radio. You can see from the sidebands, this is data that was picked up, amateur data picked up. And he can see some of the signals, and it's like by analyzing where in the mission you are, you can say, yeah, that signal pretty much looks like an accelerometer, and this is the maneuver that is happening in there. So you're actually able to decode interesting information straight from there. Another favorite one is to actually see the Easter eggs that you know, the decoders of these satellites put in there. Usually the telemetry beacons contain just plain ASCII Easter eggs for people to decode. I don't think that they tell their organizations what they're putting in there, but you know, it's fun. I think that they really put them for us. This was decoded by Root, Jacob Hruska, and he was able to actually decode a video from the downlink of Chang'e 5, which is a Chinese spacecraft going to the moon. And you could see this solar panel kind of like waving in, as the spacecraft traveled. And he was also able to write a decoder for the video until of the Falcon original flights, until SpaceX decided, yeah, we don't want people seeing this in real time, and they started encrypting the video. I was telling you as well about this stereo A probe, and the probe came by very close to Earth not too long ago in August, and you could pick up the sidebands. Amateurs developed a decoder, SatDump specifically, and also amateurs found in the documentation for the spacecraft decoder in Linux. And this is an image that I asked Fred if I could use his. I picked up a bunch of these, but I love this one. It's like you can see coronal mass ejection from the sun in those days. So picked up straight from our signals. Another interesting thing that was done is discovering Chang'e's 5 secret mission. the Chinese don't tell you what is the mission profile, what they're going to be doing. So you have to actually figure out what is it that they're doing. And this was a recovery mission. They put a lander on the moon. The lander picked up samples from the moon, returned them to Earth, and the service module that shuttled back and forth the lander then went and was parked in Lagrangian point. And suddenly we stopped seeing the service module in Lagrangian. And looking for it, Scott found what it was doing, and it was found that it entered this this interesting orbit, which is called a distant retrograde orbit of the moon, which is the first time that any nation has actually put anything in that orbit, but it's an important orbit that is being thought of for our own exploration of the moon and putting a service station around the moon. My furthest detection of a spacecraft is from Juno, when it was at a range of 616.4 million kilometers. So it took a little bit of patience to be able to pick it up. How you pick it up? Very, very high FFT resolution. So you see that the resolution bandwidth is sub-hertz. It's 0.85 hertz. This is 0.85 hertz on the signal coming down at 8.4 gigahertz. Okay. So, and then doing some averaging to get rid of the noise. My detection is by no means the record. In this class of dishes with the 3-meter class dish, UHF SATCOM, Paul Marsh in the UK, picked up Juno at 907 million kilometers away from Earth. And look at that, 1.37 billion kilometers from Earth for Cassini before Cassini was dropped on Saturn. However, definitely the all-time cup, really, truly the ultimate DX, because as far as I know, this is the farthest transmitter that is out there, is Daniel Esteves picking up the Voyager spacecraft. He was using a single 6-meter dish from the Allen telescope array. Namely, it's a little bit on the above amateur class, but he did 30-minute integration of the signal, manually tracking the Doppler every couple of milliseconds to be able to pick up that signal, but definitely world-class DX. You know, you cannot get further away than 22.7 billion kilometers away from Earth. Absolutely outstanding. So, although to the naive observer, the stuff that we do might look like watching grass grow, I think that it's a very nice hobby, especially for a club, because it demands a lot of work in very different areas. And it also has a very nice overlap with a lot of areas. So space communications, ham space communications, Earth, Moon, Earth. But even for people who are not super technical, I think that this is an area, space policy, and being able to, as citizens, police space and tell the world what nations who don't like to tell what they're doing up there is something that is definitely possible and interesting. There are a lot of, there are not a lot, there are a few, but really great resources of people who do that. I just dropped on my website, Prutchi.com, this morning, 54-page paper on all of this, if anyone has the patience to read something like that. But at least the resources are there. I also put a couple of YouTubes from some of these people who have given excellent presentations on their work in DSN. Highly recommend that you take a look at that. And I wanted to acknowledge, I don't know why the S is down there, but very special thanks to Jason Myers, KC2TDS, my colleague and friend, who is very talented and has helped me a lot with the construction of all of the mechanical stuff that I would have burned my house trying to do if he wouldn't be applying some safety norms to that and doing it carefully. And a lot of thanks to a lot of the colleagues around the world who have allowed me to use their pictures in this presentation. Thank you.